All right. Welcome to the Forum on Robotics and Control Engineering, or short FoRCE. My name is Tansel Yucelen, and I am the assistant professor at the Department of Mechanical Engineering at the University of South Florida. At my university, I am also the director of the Laboratory for Autonomy, Control, Information and Systems, or shortly LACES. With the support from my university, I am very proud today to host Dr. Frank Allgower from the University of Stuttgart to participate in our live seminar series on control systems through the FoRCE. Basically, FoRCE is dedicated to provide free, high-quality outreach events and online seminars to reach broader robotics and control engineering communities around the globe. To support our mission, we periodically invite distinguished lecturers like Frank to give talks on recent research results related to robotics and control engineering. As such, the FoRCE aims in connecting academicians and government industry researchers with each other through cross-cutting research and education discussions. We cordially hope that you will enjoy all the FoRCE events and find them highly valuable to your research interests. Before formally introducing Frank, I would like to say a few words about the WebEx, our platform. During the presentation, we are all muted, and if not, please mute yourselves. And please ask questions after the presentation. You can do this in two ways. One, you can virtually raise your hand through WebEx or simply unmute yourselves. By the way, session is being recorded to be posted to the FoRCE website. So if you do not wish to have your voice included, you can also ask questions through the chat box. You can send them directly to me, and I can read them to Frank. All right, so I am very proud today to host Dr. Frank Allgower again. Dr. Allgower is the director of the Institute for Systems Theory and Automatic Control and professor in mechanical engineering at the University of Stuttgart in Germany. Frank's main interests in research and teaching are in the area of systems and control, with a current emphasis on the development of new methods for optimization-based control, networks of systems, and systems biology. Frank received several recognitions for his work, including the IFAC Outstanding Service Award, the IEEE Control System Society Distinguished Member Award, the State Teaching Award of the German State of Baden-Württemberg, and the Leibniz Prize. Frank served as the IEEE Control System Society Vice President for Technical Activities between 2012 and 2015, and is the president of the International Federation of Automatic Control, or IFAC, for the years 2017 and 20. He was the editor for journal Automatica from 2001 to 2015, and is editor for Springer Lecture Notes in Control and Information Science book series. He published over 500 scientific articles. Well, for all of you who are here live for the presentation of Frank, first, I would like to thank so much for Frank participating in our forum. And Frank, I am now going to pass the ball to Philip, and please go ahead and start when you're ready.
Okay, thanks, Tansel. I hope now I can be heard, and I hope that soon the slide will come up. Thanks very much, Tansel, for the kind introduction and the nice words you gave. It's my first ever online seminar, and because I was a little afraid that speaking in front of an empty lecture hall or speaking in front of just a computer screen, I will not perform properly. We invited a couple of people here also in Stuttgart. So we have a lecture room full of people here in Stuttgart as well. And so we probably will have later on with the question to switch back and forth. Today I'm going to talk about model predictive control, and model predictive control is a technology that is around for many, many years and is very successfully applied, but it's undergoing changes, and this is kind of what I would like to assess today. I want to talk about what is MPC, what is MPC dealing about, a little bit about MPC theory, and then I will want to discuss with you, is the things we did in the past the right things for the future, or are there any challenges that we should specifically target. the audience is normally fairly well known. If you go somewhere and give a presentation in an online seminar, I would guess it's a very difficult thing because I have no clue who's listening. And so this presentation is very broad. So there will be an introduction to people who have never seen predictive control, and there is also people here in the audience that probably don't know what model predictive control is. So an explanation what it is up to current issues that we are talking about. So let me start first by saying a few words in general. Why should we deal with model predictive control? Now, model predictive control is one of those control methods that is really very widely accepted in the industries. In the past, in the process industries, in the meantime, also in the automobile sector, in very wide sectors, as an advanced control method, if not as the advanced control method. There are many, many applications in the meantime, and it has been really successfully applied. So in industry, people are really, they think MPC is a very important thing. That makes it, of course, worthwhile also for us in academia to look at it. And let me give you one example that I have taken from the literature. It's an ammonia plant, ammonia production. These plants are really big, are really huge, and we are talking about a lot of money. Here, this is an ammonia plant in China, where people operate this kind of plant. And there is a paper that I'm citing by Poe and Musif, and in this paper, they report about the performance of an MPC controller. Here you see the time axis from running along this axis. And here you see two control variables, and so you see the performance in the first couple of minutes. Probably these are even hours. It's 15-minute snapshots, and then in the following one. Here, a traditional controller is applied. Most likely, I would say a PI controller, but I do not know. And as you can see, the performance of this controller is such that we have fluctuations in our system. And at this time point, the controller switched to an MPC controller, and from then on we see that those fluctuations are much less. So we would say, great, the MPC controller is really much better, and indeed, this MPC controller is much better. But with this example, I already want to show you a little bit of things you can do with MPC and that go in the direction of future direction. So, of course, less fluctuations due to disturbances, measurement noise is a good thing to do. But here in this plant, you want to produce ammonium. And in ammonium production means that you want to have those curves here as high up, these are temperatures, but not beyond a certain bound, because beyond that bound, the plant is going unstable, is exploding, whatever. I'm not an expert in that. You don't want to go over it. Now, over those bounds, if you have those fluctuations here, of course, in order to stay away from this critical bound, you have to have a set point that is chosen fairly low. So there you have to stay away from this critical bound because your disturbances kick you up and down. Now, if you have less fluctuations, you can move your set point. You can move your set point to a higher set point because you are still sure that you are not hitting this bound. And that is really the main advantage in this case. And in this paper, they report about a reduced energy consumption by 1.8%, an increased productivity by 0.7%. That doesn't sound like much, but I'm sure this is millions of yen and probably also millions of dollars and euros every year. And the biggest part of that is not due to having less disturbance, better disturbance rejection, but to being able to moving the set point to a place where it's better suited. So just we keep that a little bit in mind because I will come back to that later. So in industry, MPC is very much accepted, but of course also in academia, there is lots of activity going on. It's a very active community. There are, I've written here, hundreds of papers published every year. I would say this is thousands of papers, too large a number that you can even read them. At all conferences, there are many, many sessions. There is even a dedicated IFAC symposium for nonlinear model predictive control taking place later this year and taking place every 3 years. So it's a really very active community. And maybe it's even fair to say that MPC is one of the very few control methodologies that is really accepted both by academia and by industry. So it's a very interesting methodology. Now, what is it? I hope I got your attention now, and you're saying, oh yeah, we want to know what MPC is. So what does MPC solve? MPC solves an optimization, an optimal control problem. in the sense that we have a plant described here by an ODE, but that can be absolutely generalized to differential algebraic systems, of course linear systems, to even PDEs is possible, to systems with output. So you see this more as we have a model of a system. And we want to find for that model a stabilizing controller. The first goal is we want to stabilize our system, but we also want to achieve a certain performance. And this performance is given by an objective functional that we want to minimize. An integral objective functional from the current time to infinity over a so-called stage cost that we call f, that depends on our states and on the inputs of the system. Note, for all those who know MPC, I've written infinity here. So we are interested when we have an ammonia plant or whatever you want to have, from the day we switch the controller on to whenever this plant is dismantled, to have an optimized performance. Not over some finite horizon, but really the infinite horizon is what we are interested in. And now what are we also interested in? We have to satisfy constraints on our inputs, so that the inputs cannot be arbitrary, and we can also have constraints on the states or mixture of both, such that, like for example in this ammonia plant, that we don't want to go above a certain temperature or something like that. This can be written down, in form of those of this description here. So what we are talking about is really an extremely general problem that we want to solve. A very general class of nonlinear systems that we can deal with, a very general nonlinear objective functional that we can deal about, plus we can have constraints, and very general nonlinear, almost arbitrary constraints that we want to have. So this is a very broad problem, but it's an optimal control problem. Now, how can we solve this optimal control problem? Well, there are essentially two possibilities for that, and these will both not be MPC that I will show you. I want to show you a little later what then MPC does about that. So one possibility is really that we try to find an optimal feedback controller, a U of k of x in the form, in the case of state feedback. So we want to have a map really that maps every point in our state space to an input function, and such that the closed loop trajectories are really satisfying optimality conditions. This is the classical optimal control problem, and this is a wonderful theory that leads to many different solutions. Hamilton-Jacobi, Pontryaggin's maximum principle, a lot of important things that are really associated with that. And it's a wonderful methodology, beautiful. You have a feedback, of course, because we design a feedback. It's suited for uncertainties, it's good for disturbances, it's good for unstable system, but it has one significant drawback. If you have some system that is beyond the most trivial cases, then you will not be able to compute such a feedback. It's very difficult, especially in the constraint case. So wonderful theory, by the way, a very old theory. We are talking about almost 70 years now for that theory, but you will not be able to find it. Now, what's the other approach? Well, if we are operating a system, then we don't really have to compute offline such a map that holds for all our states in the region where we are interested in. We know where we are. And so what we could do is we could use some online optimization methodology, saying where we are. So this is our state here. And now we are not computing a feedback, but we are computing an open loop trajectory. So really a u of t, not a u of x. Of course, it implicitly depends on the x where we are, but we are really computing a trajectory for our system. A trajectory that minimizes our optimization problem. So in the audience here is, of course, from Germany. In Germany, we even have two names for that. So in English, it's called both control. In German, the one on the left-hand side here, that's called ein Regelung, and the one on the right-hand side is called a Steuerung. So we have two different names in that respect. So the good news about the right-hand side, this you can compute. So if you have a big enough computer, and that doesn't really need to be so big, finding an open loop optimal control trajectory, you can compute that online. But you have a couple of drawbacks. Namely, you do not have a feedback. You do not have a closed loop controller, and that means you cannot stabilize unstable systems, you cannot deal with uncertainties. If you have the wrong model on which you base your computations, you get a wrong result. You have no reactions to disturbances. So we have two approaches that are very well known and very old, but both of them have advantages and drawbacks. And now what MPC really does, MPC tries to combine these two things. Combine the nice properties of a feedback with the computational feasibility of computing open loop trajectories. And this is done in that you are not solving this open loop optimal control problem only once. You take a measurement, compute a trajectory, and then you just implement it and go away, but that you do that in a repeated fashion. So you repeatedly online solve this optimal open loop optimal control problem. So you're solving this minimization problem over our infinite horizon. We are computing a U for the total future, for everything in the future, but then we are not implementing the whole U trajectory, but only a piece of this input trajectory. And this piece of the input trajectory for a time from t to t plus delta, this we are implementing, and then we are re-evaluating. Then we are looking what does the system do. There is a disturbance, there was model-plant mismatch, some measurement noise. We are somewhere else than we expected, and we are resolving that problem again at that time point. So we are repeatedly solving this same problem and are adjusting to where we are, this way introducing a feedback into our structure. Now, here I look at an infinite horizon problem. An infinite horizon is pretty long, an infinite horizon. So even if you have a strong computer, a big computer, then going to infinity is very long. So that's why in MPC we are choosing here a finite prediction horizon. And that's the only reason why we are choosing a finite horizon, because this gives us a much simpler way of how to compute things. And potentially we want to have a very short horizon in which we want to look at our problem in order to have really a small problem. Now, how does that look like in form of a cartoon here? So we have the time axis. Now I'm switching to discrete time. Things are available in continuous and discrete time. So we are at the present time t. So this is a past input and past state trajectory. And what we are doing at this time t, we are measuring where the system is. And then over our horizon, so over a certain length into the future, here called with this n, in the former slide I called it t in the continuous time, we are computing an optimal input trajectory, but then we are not implementing the whole green trajectory up to the very end, but we are only implementing, say, the first step of our system. And then what we are doing is, when the real time has progressed by this one step, then we are re-evaluating our system. We shift the horizon. That's why it's called the receding horizon, moving horizon control method. We shift the horizon. We keep it the same length. And now we are redoing our computations, again, over the whole horizon, implementing only the first piece, and so on. So this is really like in case of playing chess. Yeah, you have a certain situation, that's our state on the chessboard, and then you are looking ahead, you're planning ahead in the future how you want to play. If I look so in the phases here, I would say 20, 30 steps into the future. You are calculating what you think is your trajectory, but you're only revealing the first step. In my case, maybe 2 or 3, right? So you're only revealing the very first step. Then you do that step, you apply that input, and then you look what the disturbance is doing. And that's called your, the one on the other side of the table in that case. And this person makes a move, a disturbance, and then you are re-evaluating again. You're not just following your old trajectory, but you're saying again, my 30 steps into the future, I'm doing that again, and have a new strategy. I apply again the first one, and so on. So MPC is really reacting to the disturbance, incorporating a feedback into an open loop trajectory generation process. So what does the problem look like that we have to solve? So the problem we have to solve at every point in time, in discrete time, is now the following. We have to minimize over our use our cost functional with the stage cost small l over the horizon n, and subject such that the input and the states are related through our system dynamics. The starting point where we are is the measurement, and what we have to do is we have to satisfy constraints, so the x and u have to belong to a certain set here. This notation with this bar is the typical thing that you do in MPC that says you are doing that evaluation at the time point x of t, so the real time is really t, and from then on in a fictitious time you're computing what happens in the future, and that says these are the u's over this t here, which are evaluated at this real time small t here. And what you also see in this figure here is two additional terms. One is a terminal penalty term, and one is a terminal constraint that we have at the bottom here. Those will play a role later on. They are not chosen in an arbitrary way, so they are not that you say, okay, I want to have a special weight on my last step, but this will be our controller computation. This will play a role. This is the what you compute offline in order to achieve certain tasks. Now, this idea is really old MPC idea, and it's absolutely unclear where it came up. So the first citation I know of, I have to admit I couldn't read it because it's in Russian, is by Propoy from the 50s. So this is a person who has described that, and Propoy is still alive, and we have met him a couple of years back at a conference and asked, wow, you were the one who invented MPC, and then he said, no, this is really not an invention. Everybody knew that at that time, and this was kind of obvious. Yeah. So no clue who invented MPC, but there are early textbooks, Lee and Marcus' book from '67, where really this methodology is described. You can read through that yourself, that you can do that. But in that book, it also says, well, it's a nice idea, but in reality, you can't do it because you will never have a fast enough computer in order to do those computations. Well, so much to developments in the computer science. Now we have that computers. This text here is very important, because the first people who really pushed this technology forward were people in industry, and there were essentially two groups, Charlie Cutler and his group at Shell Oil. They developed software called DMC, and also Jacques Réchalet in France with the Dursa. He had a product called ITCOM, and in the 70s, in the early 70s even, they applied that to industrial methods. They didn't publish anything about it because they made a lot of money, I hope. They made a lot of money with that, and also there was an attempt to get a patent on the MPC methodology. But this patent could not be given because of the book, for example, by Lee and Marcus, because it was known beforehand. The first publications are 76, 79, as far as I know. I don't want to bet on that. Maybe there have been some other ones. But it's clear that academic research came really a little later. So this was something that was pushed forward. Yes, we can do it for linear systems, very special setups, and so on, using quadratic programs. But it could be done in reality. And then only later on, academic people at universities, they said, okay, let's have a look. Is this stabilizing? What can we do with that? And so on. So it really came later. And I would say the first people who really understood the methodology, at least the nonlinear part, are really Curdy Gilbert for discrete time, Main Mikalska for continuous time. These were the first publications where really the core of the problem, of the system theoretic problem, was really understood. How can you do systems theory for this kind of thinking? And I will show you a little bit what is the problem and how you can deal with that. So essentially, there are two issues in predictive control that you have to deal with. One is, of course, the computational issue. At every point in time, you have to solve this optimization problem. That's an effort, that's an act, and it's not trivial, and you can do this in a very stupid way, or you can do this in a highly sophisticated way. And there's a whole research community on that, and very sophisticated algorithms, very sophisticated approaches in order to solve that problem. I'm not going to talk about that at all. I'm also the wrong person to talk about that. What I would like to discuss a little bit, at least, is the system theoretic issues. So what does this method do if we apply this MPC scheme? Are we stabilizing? Is this giving us a good performance? How to deal with rejection of disturbances? How do we have robustness, and so on? So this systems theoretic problem. So, and I'm going to discuss that now a little bit to give you a flavor of what's going on. Well, and the first main question that we really have to think about is, if we just plain vanilla apply this methodology, if we take MPC, slap it on a system, we take a plant model that is good as we can, and we apply it, is the system stabilizing? And the answer is no guarantee. It's not generically stabilizing. Even if you know the system correctly, even if you have no disturbances, no measurement noise, you know the system correctly, this is not a stabilizing methodology, so you cannot be sure. Well, people, of course, immediately say, heck, before you told us 70s, they applied it, and they didn't have a clue how to analyze the stability of that, and obviously it worked, and it really worked. So what's the problem? Here's the proof. Here is an example, a first example. I will give you two examples. One example taken again from the literature, PRIMS. This is a second order system, and it's immediately clear that it's a cooked system, right? So we acknowledge that it's a second order system having one input in our state, and we have a classical quadratic cost functional. And now we are looking at the stability properties for different horizon lengths of our system. So 0.3, 0.4, 1.0, and so on. Down on the left side here, you see a state space picture. So we want to stabilize to the origin. Here is one exemplary initial condition, and these different curves here are the behavior of the closed loop, the real closed loop, not the optimization over at a specific time, and show whether we have stability. And as you can see, if the prediction horizon is 0.2, short prediction horizon, we are going unstable. If you increase the prediction horizon, then you get a stable behavior for 0.3. If you increase it further, then you get an unstable behavior. Again, if you increase it more, you get an unstable behavior. If you go even further, then you get stable at one point in time again. So a very difficult situation, right? So which one should we choose? And even if you choose 2 now, are you sure that 2 will do the job? And in fact, I think 2 doesn't do the job in that case. So this is an example of a system that shows something can really go wrong with this system. So now, this was a cooked example we agreed on. So I didn't cook it, other people cooked it, but it was cooked. Can that really happen in reality? And of course, our immediate reaction is reality is not cooked. This is more engineered, or it's more natural, so it won't happen there. But yes, it also does. And now I show you a second example, and that example, here the audience, many of the students know that already. So this is our 4-tank system that we are using in our control courses. I would say this 4-tank system, the control of the 4-tank system, is probably the most boring of those lab experiments that we do our teaching with. You have to wait a damn long time before you see something, and then you actually don't see much in that system. So this is really a slow, boring system, and it's pretty much stable system. You know, to do something bad to that system is a really big problem. Now let's look at this system and do a plain vanilla MPC controller. Again, nothing cooked in that case, just using a cost function that makes sense, using a prediction horizon that makes sense, and let's apply the resulting controller to this boring system that we are having. And here you see the results. So this is the solid line here, up to 150 seconds roughly. This is the experiment. The gray line is the simulation, so that you see it a little better. And you see the heights in the 4 tanks for that system. And it's a standard setup. We're using a prediction horizon of 1 minute. This is pretty reasonable for this 4-tank system. So that is not a short prediction horizon. This is a reasonable prediction horizon for that system. And what you can see if you apply plain vanilla MPC, that after 150 seconds, the 4th tank here gets to 28 centimeters. 28 centimeters is the height of the tanks. If you go beyond that, then you have a mess in the lab. And that's why also this experiment here is stopped at that point in time, because then the tank would flow over. The simulation you can carry on, so it's truly an unstable behavior of that system. So standard plain vanilla MPC without any tricks, with a horizon lengths that make a lot of sense, is not stabilizing this slow, boring 4th order system that we are having here. And of course, that is a little bit shocking, right? So would you now go to this ammonia plant and apply your methods and say, okay, well, if we don't want to go beyond a certain temperature, otherwise it explodes? Probably not. So here you can see that this is really not an artifact. So here you can see a couple of more curves, now all in simulation. If you increase the horizon length further up to 135, it's still unstable. Only if you go beyond the 135, then it's getting stable. 135, a little more than 2 minutes. This is normally not how much students would want to wait for the control to see the control behavior in their control lab. And I will come back to that in a second and show you that it is indeed possible to have an MPC controller with a short prediction horizon of only 60 seconds that is stabilizing that system, but not just applying MPC, the plain vanilla MPC stuff. So, well, we could now say, all right, so we get a control behavior with an MPC controller. Let's just analyze the controller as we normally do. We compute it, right? And then we analyze the controller, and if it's stable, all right, we won. If it's not stable, we do something. We increase prediction horizon or something like that. But how would you want to do the analysis of the stability of this control system? We are not getting a controller, right? What we are doing is at each step computing a trajectory. From that trajectory, we take the first piece. The rest we are throwing away. And that's it. We have no u equals k of x that we could plug into our system, linearize it, look at the poles, or do Lyapunov theory in order to get stability. We do not have a controller. So analyzing the stability of the closed loop is just not possible, period. Second thing is, of course, we are smart. Yeah, but we are predicting into the future, right? So we see where we are going. So let's just look if all my trajectories are heading to the origin. What can go wrong, right? All of them, I do a simulation, an optimization in the future, and almost goes to the origin in my finite horizon. What could go wrong if at each point I'm going in the right direction? Again, not true. And I want to show you that with a little cartoon again. So even in the case now that we have no model plant mismatch, so we know our system perfectly. We have no disturbances, nothing else. So really the best ideal case, then the predicted open loop trajectories, the result of our computation, will not be what we see in the closed loop. Now, what's the reason for that? Here is again our state space. The origin is where we want to go to, some initial condition of our system. Let's first look at the infinite horizon problem, the one we are actually interested in, right? If we could solve the infinite horizon problem, then this is our optimal trajectory that would go to the origin, this green curve here. And if we now implement the first piece of that trajectory and redo our computations at that point in time, then the result of that computation would be the same trajectory again. End pieces of optimal trajectories are optimal, Bellman's principle of optimality. So in that case, the predicted open loop trajectories do coincide with the real closed loop trajectories that we are having. Now let's look at the finite horizon. This is the one we are solving here in MPC. So we only look into the future over a finite horizon. We do that because we don't want to compute so much. We have a fast system, and we cannot really look for a very long horizon. Now we do our optimal computation. This is this green curve here. And now I'm implementing the first piece. And because I have no disturbances, no model plant mismatch, I'm, of course, also following that trajectory, the same as before. But now, if I'm at this new point and I'm re-evaluating my trajectory, I have shifted my horizon. I'm looking further in the future. I'm seeing something that I have not seen before. Maybe, you know, here has been a disturbance. Not a disturbance, a constraint that I cannot go through. That could well be, right? I didn't see it before. And then I have to now re-evaluate. Or there is some behavior of my cost function. So the solution will not be the same because I look over a different horizon of my system. Then I'm implementing again the first piece, look again at the solution, and that will differ again. So my predicted trajectories are not the ones that I'm following. The ones that I predicted at the first place are down here. I'm now staying up there. Now, what does that mean? So implicitly in MPC, we were really hoping to solve this problem down here, the infinite horizon problem, over a certain stage cost. This was our hope that we started out with optimizing. And we do that by minimizing repeatedly the same objective functional, just with a finite horizon, but with the same stage cost function, hoping that if we do that, then this is a solution to our original problem. But now we already see the trajectories are not the same, right? So we are not following the same trajectory. So repeatedly solving that problem down here does not give us a solution to the problem above. So from a first result, we are talking about stability at the moment, I know, but the first insight from this, that the predicted trajectories are not the same than the true trajectories, is we are not solving the problem that we want to solve. We are solving something else. So we have a problem here. Now, and also, if you do this game further, now that you are not really getting a solution from this cartoon, you can see that you're really not guaranteed to be stable. In that case, you would just have a limit cycle, but you can easily, and it's easily possible to cook up examples where you really go to instability, even so that every trajectory points in the right direction. So we have a true problem. So we cannot guarantee with this methodology anything, not that we solve the problem at hand that we want to solve, nor that we have stability. So the question is really how to achieve stability. And I just want to let that sit for a second. It's not a simple problem, right? And it really took academia a long time in order to come up with a solution. It's not a simple problem in order to solve that, because we have no means of even analyzing it. Now, but of course it can be done. And one of the things that we just saw already, and that is very well known in the MPC field since its very beginning, if we have a large horizon, so if we go almost to infinity, so if we are really close to the origin, everything is fine. So with a very large horizon, things are not problematic. We get good performance. And then, of course, what I'm just saying, the trajectories still differ, but they only differ by a little bit. But that is, of course, not what we want to do. We don't want to just have a very, very large horizon, because we want to do our computations fairly fast. So we want to have a formulation, something else that gives us a solution to that problem, so that we can guarantee stability, hopefully also address performance, despite the fact that we are giving a short prediction horizon. So for the stabilization problem, there are essentially two solutions, two possible approaches. One is the approach that's called guaranteed stability. And the idea behind that is, okay, we already saw if we repeatedly are solving this finite horizon optimization problem, we are not getting the solution to the real problem. Let's alter the problem. Let's take a different stage cost function. Let's look at a different problem and choose that such that we get an approximation to the true system. And that is called an approach with guaranteed stability in MPC. And what you are essentially doing, you're introducing this terminal costs and terminal penalty terms that I showed you before. So these are called the stabilizing ingredients or the stability constraints of your system. So what you are doing is you are designing offline beforehand appropriate terminal penalty terms and appropriate terminal constraints, such that if you solve this problem with those additional two items, that this is an approximation to your old problem and for which you can give a guarantee. There are many approaches how you can do that, and this is a fairly old technique. So here you can see this was the 90s of the last century when people were working on this, but this is still a problem that is actually actively researched about. Here is a result from quasi-infinite horizon that we have done, and that gives you just a feeling for how things work. So this E and this epsilon here, it's a continuous time case now, so I'm switching back and forth. Maybe I claim now this is in order to demonstrate that everything can be done in discrete and in continuous time. So I did that by purpose, that I'm going back and forth. And you can have the following result there. So if you compute those terms, E and epsilon, in a certain way, namely such that this condition here is satisfied, what you want to have is that within this region, epsilon, around our origin, within this region, you want to be able to find an input such that this control Lyapunov function here is satisfied, that has this E term here, and that has the stage cost up there. So you have to compute it in order that this is satisfied, and those people who are into nonlinear control theory, they immediately see where this is going to. And but I'm not going into that here at all. But if you have a second thing, namely that the optimality is feasible at the initial time, then you can guarantee that your feasibility, you find a solution to your optimization problem stays. That's called recursive feasibility, and that you indeed get asymptotic stability, and that all points for which your optimization problem is feasible at the initial time is a subset of the region of attraction of your problem. So you are really getting stability. And the beauty is that this E and F that now looks fairly complex here, you can compute it. And I'm not going through that at all. You know, you can first do that, second do that, and fifth do that. And these are all fairly simple steps as compared to the very general problem that we are looking at. And you can compute those ingredients here offline beforehand. And then you know with those ingredients, you really get a stable closed loop. Let's recall our lab experiment here. Now, remember, with t equals 60 seconds, 1 minute, the system was unstable. Now we included those stability constraints, the quasi-infinite horizon constraints, the E and the epsilon. We included in the same problem, changed nothing else of our system. And as you can see, everything is going fine. We have a stable closed loop, as we have proved before. So it's not really surprising. But this is a stable closed loop for our system. Okay, that is one approach. The second one, looking at the time I'm skipping, the second alternative is you try to find the minimum prediction length that you have to use going close to infinity in order to come to a solution. This is a much younger approach. It's called unconstrained model predictive control. It's actually the worst chosen name that you can imagine, because this is a problem where you can have constraints on your inputs and so on, but you don't have stability constraints in your system. You don't need the E and the epsilon. You're just calculating a prediction horizon length that guarantees you to be stable. And this can be done, and it's a very interesting methodology where you can come up with a fairly conservative result. But these are much younger methods here. So we are now talking about really fairly recent results, how to do these kind of things. And both approaches have advantages and drawbacks. Let me go through that a little quicker. And I promised at the beginning that I want to tell you also a little bit where are we moving to. Now, where do we apply our controllers? At least here in the Stuttgart area, where we have a lot of machine production industry and car production industry running around, we are dealing at the moment a lot with what's called Industry 4.0. So Industry 4.0 is the idea that you do a production operation where you go away from this sequential production where one thing after the other is really sequentially done to a more flexible production where you have your production stations that can do a lot of more things. And for each product by itself, it's determined online how that is assembled. So maybe makes no sense here, but you first put the steering wheel in before you put the wheels on the car, or something like that. You leave that open depending on which station is available, who can do what, whether the person ordering a car wants a steering wheel. In the future, that may just be an optional item, right? And so we really have a much more complex system. So we have stations that are not pre-calculated, where you have a controller that you put in a lot of effort before, and always they perform exactly the same thing, operate at the same steady state. I'm using that technology now. But what they are doing different things, and at different points, whether you order a Mercedes S-Class or a Mercedes A-Class is a different kind of thing, but the same production station can deal with both cars. So essentially we have this whole mix of production things, and they talk to each other, and each time they do something different. So if from a control point of view, what we have is a network of systems in which a dynamic network of systems in which we are producing something. And each of those nodes is controlled, but now they are not always doing the same thing. So if you once pre-computed something at a steady state, then if you have another thing to do, this steady state pre-computation, this E and the epsilon, they are the wrong ones for your new task. And also if you say, okay, it doesn't matter, I do it anyway, then you will get to a very suboptimal result in your system. So, and this can be a little bit generalized, right? So far, and we are now looking again only to one plant that we want to control. So far, we want to stabilize it at a predetermined steady state. This was our goal. But here in this Industry 4.0 context, we want to achieve, well, that it should do something as optimal as it can, and that's not necessarily going to the pre-computed steady state that you have. And so what we want to do is get away from having a set point before, having a cost function that is positive definite around that set point, which is a requirement. I forgot to mention that in order to really prove that it's a stabilizing MPC scheme. So if you go away from the steady state, your cost increases. But we don't want to have that. Maybe we want to just put in euros for our individual costs. Do something as to earn as much money as you can, and then the best performance is certainly not at a set point, but infinity sounds pretty good for in terms of euros. So and this is called economic MPC. So you're not giving a set point. You are only saying I have a system. I have an objective functional, minimizing energy, maximizing euros, dollars, yuan, or whatever you want. And the cost function is now, of course, not a positive definite function. And solving that problem in an MPC framework is, of course, possible. You just slap it in, and you say, solve me, give me open loop trajectories. I look over my finite horizon, and then I implement the first piece of my trajectory, and then let's see what's happening with that system. So it's really easily possible just applying that. And now the question is, of course, what properties does a system like that have? Of course, as I try to motivate, this makes a lot of sense. You know, if you have a chemical production facility and you have a disturbance that you have more initial reactant in your reactor, a classical controller says, catastrophe, we have to get rid of it. An MPC controller would say, wonderful, let's produce more, sell more, and we have more dollars. Refrigeration system, if the outside gets colder, it's a good disturbance, right? So we like cold. And if in the production system, Industry 4.0, we of course have that naturally through the different properties that we are having. Now, so far the stage cost was positive definite. Now, if it's not positive definite, if we just look at this kind of performance, what is happening in our system? What kind of behavior are we getting? And especially, where are we converging to? What's going on? So with the set point, of course, we go to the set point. But here we have no set point. And it's well known, at least in the process industry, that indeed the optimal operation of systems doesn't have to be a set point. If you compute the optimum could be a trajectory. So this is, if you just want an optimal operation of this reactor, then this is the optimal result. And this would also be the output of your MPC controller that you are getting. And of course, if you are having a system, let's say our 4-tank in the basement, and this is the optimal way how to operate it, you would like to know beforehand so that you should stay a little bit alert. So, and the second question is, of course, when you have, if you have such a kind of behavior, are you going to that? Or if you are not having that kind of behavior, if you are having an optimal new set point that the system finds itself, are you approaching that set point? Is that kind of guaranteed? And that is now the new MPC theory that we are talking about. And I will go again over that much more faster. So you can really analyze the MPC controller in that respect. So as we have done before with stability, we now analyze and we ask the question, for example, what is the optimal operating regime? Will we have these fluctuations, or will it be an optimal steady state that we don't know beforehand, right? But will it go to that optimal steady state? And the interesting thing is that this problem can be solved with tools that this analysis problem can be solved with tools that we know, namely dissipation inequalities. Again, for reasons of time, I'm not going into that. Everybody knows dissipation inequalities. Lyapunov function is a dissipation inequality. You can check L2 gain, ISS, stability. You can do almost everything using dissipation inequalities by having different supply rates for which you have to find a storage function. And now asking the question whether our optimal behavior converges to a set steady state, to a set point, or whether we have a fluctuation, we can also answer, namely by looking for a solution to a particular dissipativity inequality with the supply rate that is just the cost function of our stage cost function of our system minus the stage cost evaluated at the optimal steady state, for which we don't know whether it's the optimal operation. A dynamic one could be even better. And now the result is indeed a necessary and sufficient result. This is very interesting. Lyapunov, for example, as we all know, is only sufficient. This is a necessary and sufficient result to our system. So if there is a solution, if this dissipation inequality is satisfied, if we can find a storage function, then we know the optimal operation will be a steady state. And you can compute that beforehand. So, and you now ask a question, are we converging to this behavior? So will our MPC controller go there? Now, if you're demanding strict dissipativity, then you can prove that you are indeed converging to that system. You can also answer other questions, namely whether you want to go to a periodic behavior. Then you just have to choose a different supply rate, a p-step related supply rate. Don't want to explain, and everything holds also true. So the good news is, even though this is a completely different control problem from everything we have so far, still the tools and methods from the control community that we are having can still be applied in that framework. We don't have to have a completely new control methodology at hand. So you can do that under constraints there, under disturbances. There it gets even more interesting, namely operating a system. So this is the cost function over possible states here where you want to operating it. Here it's clear the best operation is here. So our economic MPC controller would go here if we tell him, the controller, tell her that we want to have an optimal behavior. But now if we have disturbances, then of course we are not operating at that point. We are going back and forth between our system. And at some size of the disturbance, it may be much more economical to go to a different place just for operation. And this is something that we also hope in an economic MPC framework we are taking care of. Automatically, the controller would go to the right one. And this can also be done. The larger, of course, the disturbances are, the better that gets. And you can do many different things. You can have many different assumptions on the disturbances that you have. And I want to just flash one picture to be able to mention one approach, namely tube MPC. Tube MPC is a methodology I'm not going to talk at all about, but that allows us to talk about robustness in MPC problems. Not only for economic MPC, but also for the classical stabilizing MPC. So tube MPC is one of the thinkings. And if you are interested in finding more out about that, that's the word to Google or to find the papers on. What we of course have in the framework of Industry 4.0, we not only have one plant, but we have many, many plants that are interconnected. So we have a network of dynamical systems. And now the question is, can we have these individual economic MPC controllers for each of our plants? Then we slap everything together over our network and have a distributed MPC solution. So the controllers talk to each other, yes, but it's not one big optimization problem that we are solving. We are only exchanging certain information. And now the interesting result here is really, yes, it can all be applied. We can have a setup here. It's not trivial and too much detail for a general talk the way I've given, but you can really find a setup such that even in a distributed environment, you are going to the optimal behavior of the overall system that you have. And even this thinking with dissipation inequalities, what kind of behavior will we have at this optimum for the whole network of systems, is still governed by dissipation inequalities. As I'm running out of time, you see I had a little more ideas. I'm jumping to the end, and what I want to do is saying, okay, the world around is changing. The control problems are changing. It's getting more and more competitive. It's getting more and more flexible, more and more online computational possibilities. So what we are having is this network of systems that somehow interact. And yes, this introduces new challenges, namely no pre-computed set points anymore. But we have to deal with somehow an optimization of something that can lead to more general behaviors. And secondly, we can say, yes, MPC provides us very naturally with this kind of methodologies. And not only conceptually, that you can set up these optimization problems and just say, let's see whether it finds our solution, but that we can also find an MPC systems theory and MPC control theory such that we can really give guarantees that this behavior is the one that we are really expecting. And this really brings me to my closing slide here. So I think in this old field of MPC, that is really a very successful field for classical control, there is lots of things going on even at the moment. Lots of things that are not just filling the gaps and doing the epsilons and deltas to find the last little things that can be done, but there are exciting new developments in this area, exciting new developments that really also make it necessary to have active research in that field. And I think that is really one of the bonuses of MPC, and of course in an environment where the industrial relevance is really high. So let me acknowledge all the results that I have shown were not my own. They were by Matthias Müller, assistant professor here in the Institute, Florian Bayer, former PhD student, and Philipp Köller, a current PhD student. And Philipp, I have to really thank you very much. This would not be possible because he's the one who is running this whole show here, at least from the Stuttgart side. Tansel is doing that from the Florida side. All the technology that you hopefully could hear me and see especially the slides, this is due to Philipp. So thank you very much. And with that, I would like to end my presentation and give the general audience, wherever you are, the possibility to ask questions, and of course also the local audience. Thanks very much.
Thanks a lot, Frank.
So Tansel, I think now it's your turn again, right?
So we can keep the camera on you. So let's see how we can do that. So I will keep the ball on you just in case for some questions you may want to go through your slides. So we still need Philip. So all right, now we can ask questions. We can do a couple of ways. You can unmute yourselves, or if you like, Frank, we can start questions from your side.
Okay, shall we do that? Start with questions from the audience here. Anybody here having any questions? This audience here is very particular. The audience here consists of students, master students, who for the first time have heard MPC, I assume, at least some of them. And then there are also people in the audience who do research on MPC. Yeah, so it's a very mixed audience. Any question here? Yeah, please.
Yes, at one point you talked about that you linearize your set point and then compute around this set point. But then you need to, if you move out of the interval for which the linearization holds, then you need to recompute it, right? Or what do you do there? I was just wondering that.
Okay, very good question. I repeat it again, Tansel. That is the idea, right? I repeat the question.
Yes, please.
Or could everybody hear it?
I could not.
You did not. Okay, so the question was, okay, we are back at a stabilizing world, so we have a set point, and we did computation now of this epsilon and e term around that set point. But now if we are moving around in our world, then one point in time we are moving out of this linearization range of the system, and now what happens there? Well, the answer is nothing. We are really in the nonlinear world. So if we have that setup that I showed you with a nonlinear system, a set point, then we are really computing those terms such that if you find a solution to your optimization problem, so if the optimizer says, yes, I find some solution to that problem, then you know from that point on to the origin, you will have really a stabilizing solution. And one thing that I also forgot to mention, if you use quasi-infinite horizon, then you are even approximating with this way the infinite horizon optimal control problem. So no problem really, we don't need to know anything around that. We use the linearization in quasi-infinite horizon in order to compute the terms, but this can also be done in a nonlinear way with other methodologies. It's a truly nonlinear methodology. Tansel, there are no more questions here. Must have been a perfect talk, right? No questions.
Personally, your talk was always perfect. But I have a question here on the chat.
What?
I would like to read it for you. So, okay. So Nasibe is asking a question. I got another question. So the first question is, he was wondering, what is the common or best optimization method you are currently using for the nonlinear MPC?
Okay, well, we are control theory people here, right? We are using FMinCon in MATLAB, but that is definitely not the best method. But seriously, I should not answer that question because there are really experts out there, and there are different different software solutions around, and there are excellent people doing that. And the best way is really to Google, and there are really professional solutions by various people. Most of those are even free of charge, so you can really download them. But I don't want to answer which is a good method or the best method. They are all very good and all have advantages, drawbacks for the application. Is that fine as a non-answering that?
That's perfect to me. I mean, if Nasib replies, I will let you know. So I have another question from
people can, sorry Tansel if I interrupt, if people are really not in a public way like now, if they want to know what to use, send me an email and I point you to a couple of software tools that I like, just not publicly saying one is better than the other. Sorry.
Sure. And Ehsan Arabi asks a question. Are there any MPC methods that integrate, for example, robust adaptive control theory to deal with uncertainties?
Okay, yeah, so that is, including things is the power of MPC. You can do MPC with everything. You know, learning, to take another keyword, is wonderful in connection with MPC. So yes, there are many solutions around with applying adaptive technology with robustness and so on. So doing it conceptually is really something in MPC where you are given a lot of flexibility. Where it gets a little more tricky is if you want to prove something, convergence, that your adaptation converges and so on. And in that respect, I'm not so 100% sure whether the combination you mentioned, so robust MPC together with adaptive, there are too many results around.
Thanks, Frank. So I am receiving a lot of questions. One more question. So Dohang Daniel Yoon adds to Ehsan's question, and the question is, have you considered any stochastic approach along with your model? And how will that be possible?
The stochastic MPC, really as a keyword, is one of the big areas in the MPC framework. There is lots of going on. This is really a topic that is very hot at the moment. And we also have people here in Stuttgart working on that, not at the moment here in the audience, but there's also a PhD student here. Yes, this is definitely an approach. And again, from various sides, so more from how can you prove that things go well, to how do you do the computations, where is the validity, up to really applying it and seeing how good that methodology is. Yes, stochastic MPC is definitely a very hot and interesting topic. And you searchable for the keyword stochastic MPC. There are stochastic MPC sessions at CDC, for example.
That's correct. So I am receiving more questions. So could Dr. Allgower comment on the general relationships among MPC, optimal control or functional analysis? Question from Quinpin.
Okay, wow. Thanks very much for that question. Functional analysis, very useful thing like optimization, optimal control, and MPC. Well, I tried to show the connection between optimal control and MPC, that we are trying to approximate an optimal control problem using this MPC thinking. Now with functional analysis, yeah, well, I'm sure there is connection. So we are using functional analysis, but I cannot really answer a direct link to that. Sorry.
One more question from Yuan Tink. I want to ask Prof. Allgower about his idea on the comparison between contractive MPC and quasi-infinite prediction MPC.
Okay, contractive MPC. Well, I didn't explain too much in that area. Contractive MPC is an MPC approach, by the way, also going back to the 90s, where this idea of having stability constraints was really applied in a very good way. The idea behind the proof of the stability proof of all that is you take the value function, the optimal cost that you are getting, as a Lyapunov function candidate, and you prove that the value function really decays, and this is the core of the stability result. Now, if your optimal cost function should go down, one of the possibilities how you can achieve that is just put it as a constraint, saying, okay, my cost function at the next time point has to be smaller than the cost function before. And so we are putting that as a stability constraint in our optimization problem, only allowing solutions that satisfy that. And that's called contractive MPC. So you're really demanding a contraction. And contractive MPC works perfectly well, but it has one drawback. Namely, in MPC, what you really have to do is you have to show recursive feasibility. So once I found an optimal solution, once I found some solution to my optimization problem that satisfies the constraints, including the stability constraints, then I want to be sure that from then on, if I follow my trajectory, this is not stopping at one point in time, that I always find a feasible solution. This is called recursive feasibility, and this is something that we are always proving, quasi-infinite horizon, and that is the key step that we prove recursive feasibility. With contractive MPC, you cannot prove recursive feasibility. In fact, you can show that recursive feasibility is not satisfied. So as long as you find solutions for which you can have that contraction that you are demanding satisfied, everything's fine. But it could well be that in the middle of your operation, suddenly the optimizer says, sorry, can't find a solution. There is no feasible solution that satisfies our constraints. And then, of course, you have no stability anymore.
Thanks, Frank. So I am receiving many questions. So I am, by the way, from the audience, so I am sorry if I missed a couple of questions. I am trying to rephrase some of the questions and combine several questions with each other. So one question asked by a couple of people, including Ali Albatat, Dina, Irofi, basically they wonder how to guarantee stability by using economical MPC, and what happens, for example, in the presence of time delay, so on and so forth. More like a stability questions of economic MPC.
Okay. Very good question. So compliments to those many people, obviously. So this is something that I skipped, and I made it much too easy. Of course, we also need stability, additional stability assumptions in the setup that we are having. And it's roughly the same as for stabilizing MPC. I just skipped that or left it out, actually, even if I would have talked a little more detail. There's no slide for that. And the reason is that I wanted to focus on the core difference. But yes, you also need stability constraints, something in that direction in order to have the proper results for the economic MPC.
Thanks, Frank. So one more question from Craig Bill. He says, I have been investigating, but have not seen much in terms of work that looks at how to manage the responses of an MPC controller when you are estimating the parameters or bounds of the problem online. So the problem changes at each time step. As a result, the MPC controller can exhibit chatter or oscillation, limiting the rate of change, or the actuator works, but then reduces the controller performance. So Craig wonders if there are other ways making the controller less prone to, for example, noise effect.
Okay, but this is also a similar question to the one we had before, right? So using adaptation in some sense together with MPC, a very natural thing to do, and that makes a lot of sense. But of course, it depends very much how you do it. You know, if you have a very aggressive adaptation scheme, the result will be very different from having something very modest. And there is lots of practical things going on, but as I said before, fewer things that hold from the theoretical side, but I would recommend in that respect, I'm not an expert on that, really to look into the classical adaptive control literature. So the thinking should be really the same in that respect. Very valuable, and I believe that this can really go wrong if you combine those two things. One more reason to have good MPC theory.
Thanks.
Tansel, you said before when we discussed, you said there was most likely no questions. It's fine, you know, it's 7:05 in Germany. We are still not very hungry. So I'm available for more questions, and I'm actually happy that people ask questions.
I mean, since audience found you, they would like to keep you, probably, you know. Maybe, you know, I will ask, I mean, certainly there are a lot of questions are coming, and it seems like they are not going to be over. So I will read one more question, but then can they send their questions to you to discuss more offline?
Okay, you can definitely send the questions depending on the amount of questions. I may be very busy answering them, so let's better not have the sending, but I'm very willing to answer a few more online here. That is, I'm a slow typer. Actually, I'm not thinking about myself, I'm more thinking about the audience here.
Sure.
So address to the audience here. If you think you have heard enough about MPC for today, feel free to leave the room. I'm staying here to answer the questions of the online audience. So please go ahead, Tansel. Sorry for that.
All right. Oh, no, perfect. So one more question then, maybe one final question then. How much is actually mixed integer programming used for non-convex MPC in practice?
Oh, that is used quite a bit. So especially in the process control environment, I would say since more than 20 years, people are really, really doing this. So this is really widely used. Again, we should distinguish between using it, applying it, and successfully applying it with a real benefit, and then being really able to prove things. So on the system theory proof side, I think there is much, much less going on. But from a point of view that you do, for example, design decisions, whether you switch a valve on or not, whether you use a part of your plant or not, this can really give you the big margin in your performance of the system. And people realize that very early on. So just to mention one group of researchers here, it's at Imperial College. There are over many, many decades very successful applications in the process sector in that direction.
Thanks a lot, Frank. So with this, I would like to end, but first of all, I would like to thank certainly first Frank. Thanks so much for participating in FoRCE. I would like to thank your audience there, probably at 20, 30 people.
Me too.
I also would like to thank 130 plus people online and for a lot of good questions. And thanks all. So that perfect talk, perfect speaker, everything was perfect. And it is a little bit late in Germany, but thanks a lot to you and your student staff for accommodating this late night MPC talk for us.
So it was a real pleasure also from my side. Thanks very much for inviting me to give this presentation. I very much enjoyed it, and I think this is an excellent format. Now that I have done it, I can only recommend to other people in the field to really be part of that. I would also want to add one thank you to your list, and this is Philip. Thanks very much, Philip Köhler, for your support here.
Yes, thanks, Philip, too, so for making our life easier. And we have Emre. I would like to also thank Emre. Emre was making my life easier here, too. Yeah.
Okay. Thanks, Emre.
All right. Thanks, everyone. Thanks so much, Frank.
Okay, bye-bye. So we are muted now. We can speak freely.
Yes.
Okay, thank you very much. Bye-bye, Tansel.
Bye, Frank. Take care. Coding.